Hi everyone, welcome to today's webinar. My name is Brigitte Farah. I'm from the Metallurgy and Materials Society of CIM. And today we're presenting Mining Value from Waste, from Concept to Reality, with our presenters Janice Zinck and Rory Cameron from Natural Resources Canada. Before we begin, I just want to go through a few housekeeping notes to ensure that you have the best possible experience. So if you dialed in with your computer, ensure that you have the computer radio button clicked. And likewise, if you used a traditional phone, ensure that you have the phone call button selected. So at any time throughout this webinar, if you have questions about the content or even a technical issue, use this question box here to place your question, and we'll be holding them until the end. As well, we will be conducting a poll or two, so ensure that you participate. So today I'm not alone. I'm joined by my colleagues Laura Foley of CIM. Hello. As well, I'm joined by Nolene Ahern from Barrick Gold Corporation and the Environment Section Chair. Of course, we have our esteemed panelists, Janice Zinck, CanmetMINING of Natural Resources Canada, and Rory Cameron of Natural Resources Canada. So we will begin, and I will turn it over to you, Rory and Janice.
Good afternoon to the people in the East. Good morning to those in the West. Hope you can hear me well. This is Janice Zinck, and I'm with Rory Cameron. We're going to present to you a bit about our new initiative called Mining Value from Waste, from Concept to Reality. And we're going to talk a bit about the background of this new initiative and some of the early progress. And then we're going to get into some of this more specifics and technical aspects of mining value from waste. So looking at some case studies, and then Rory is going to present on some of the R&D examples that we've recently undertaken. And then we'll get into hopefully a bit of a good discussion. So for those of you who may or not know about mine waste in Canada, if we just look at tailings alone in Canada, in general, we produce some 200 to 250 million tons of tailings a year, and 90% of that is from metal mines. Most of the contributors are base metal, iron, and gold mines. So not only does this offer an economic opportunity, as you can see in the next slide, there is also the environmental side of things, which I'll discuss later. So if we just look in terms of metal worth that's in gold tailings, where we've estimated that from our database on tailings inventory around at least $10 billion US. And in terms of pyrrhotite tailings in the Sudbury area, again, another $10 billion just for the nickel in that. So you can see that there's a huge economic opportunity to look at how we can extract the value from these tailings. But it's not just about the economics. It's certainly also about the environmental side of things and liability. So the liability alone is another huge aspect. So many companies and many governmental jurisdictions have to manage these waste areas in perpetuity, and they post huge financial bonds. So not only is there the liability, but many of the times the liability associated with these mining waste is not actually well calculated. It's often, a lot of it's unsecured. And we often see that in many cases when we look at the care and maintenance, or we look at the management of these wastes, that the costs in the end far exceed the original estimate. So if we look at the example of the Faro mine in the Yukon, we see that the costs now are estimated at over $1 billion to remediate that site. So if we look at how we can manage these mine wastes and how we can extract the value while reducing the liability, and that's really about this mining value from waste project. Also in terms of when we started looking at whether or not we can reprocess the material, we looked at what was some of the drivers behind the processing opportunities. And in most cases, it turned out that it was the metal price, which was the real driver in terms of the opportunity that existed. So that's something we can't necessarily control, but we can certainly control things like the technologies that we use to be able to extract the value from the resource. So now we're going to move into a poll question just to make it interesting and interactive. So I'll pass it back to Bridget or to Laura to ask the poll question.
Sorry, I was on mute. So yes, here's our first poll question. What do you think is the greatest barrier to reprocessing mine waste? So plug in your answers. Economics, regulations, transfer of liability, technology, or other. So we'll give it a few seconds for people to vote. I see the votes are coming in. And we're almost there. Oh, okay. Oh, I will be closing. Is there anybody else? Okay, well, it looks like we have 81% of you that voted, so we'll close this off and see what our results are. So the results, Janice, are 36% economics. So back to you.
37. So the economics was the biggest driver of the poll question, Bridget?
Correct. And the second one was transfer of liability.
Transfer of liability. Good. So this is very much in line with what we've heard. We've gone out to consult with stakeholders to see what they see are some of the major challenges in around waste reprocessing. And certainly the economics was a huge driver. Certainly around the CapEx and OpEx around the operations. But there were also a number of engineering challenges, which I didn't put in my poll question, but how do we actually reprocess these wastes? How do we manage the throughput? What do we deal with variable feeds? How do we control deleterious elements? And how can we have on-site demonstration? But some of the other barriers were regulatory, and this certainly includes things like the transfer of liability, but also the regulatory support for initiatives like reprocessing. So just for a concept, this is the concept for mining value from waste. So it's looking at taking these high liability waste, extracting the metal content and extracting the value, repurposing them, and also addressing the environmental and social risk associated with them. One of the benefits to doing so is that we're already looking at a pre-processed material, so there's a lower energy demand in processing these materials, and ultimately we produce an end product that we can then use to use in other applications. So there's opportunities around a number of different resources that we can extract from the tailings or from the mine waste. And then there's also byproduct opportunities. So those can be in terms of looking at the silica sand, looking at fills for concrete, or for looking at reclamation opportunities, using the benign material that's left behind for reclamation opportunities to produce biofuel and bioenergy crops that can then go back to kind of feed the process, to provide community energy, and to reduce the cost for reprocessing. So there are a number of benefits for this approach, which are articulated there on your screen. So in starting this initiative, which is early days, we were using the National Collaboration Strategy that was released last August at the Energy Mines Ministers Conference. And this was a strategy that was put forward to look at how we can accelerate innovation through collaboration. And so we use this strategy. In fact, we're piloting the strategy using this program. And this strategy set out really three main areas, which was to build a culture of innovation for a clear and collective measurable target, to share resources and leverage existing strengths, tools, and organizations. And again, look at culture around communication and collaboration. So in laying this out, we undertook a number of different steps, looking at what were the important things to use, how do we use collaboration in trying to accelerate a program around mining value from waste. One is a collective goal. One is looking at how we can, what are kind of the projects that are currently out there so that we're not duplicating effort, and what are joint funding opportunities. and how we can better communicate the activities that we're doing. And so this is where we started out to try to develop more of a pan-Canadian effort in around mining value from waste. The first, I guess, formal gathering was in December in Toronto, where we had a workshop to try to bring together individuals to start to talk about this area. And really, because there are a number of individuals and groups across the across the country that are working in the area of reprocessing and repurposing mine waste, and no sense for us to work separately. We need to work collectively and really to kind of accelerate the progress. So in this workshop, we had a number of excellent presentations, and we worked towards kind of coming up with a common objective, and also to looking at the opportunity to be able to kind of pull together the collaboration amongst small groups to submit a number of clean growth program funding applications, which I'll talk about shortly. So at the December workshop, there were a number of areas of focus that were presented and validated. These are listed here, which include reduce the environmental liabilities posed from existing mine waste, look at recovering the metal values from the waste, produce benign tailings residue, and utilize the mine waste as a resource and look at those byproduct opportunities. And then behind all of that was certainly the policy and the regulatory support to be able to make this happen. So at the workshop and afterwards through a number of discussions, we've tried to put together a common objective of what this initiative is, its ultimate goal is. And this again was validated through conversations, and essentially right now it stands at a Canadian effort to develop the tools, technologies, policies to de-risk and accelerate the demonstration and full-scale waste reprocessing and repurposing projects, with ultimately the goal to reduce mine waste management, mine waste liability, environmental impact, and while providing local and national value for Canada, such as jobs and resources. So that's the common objective, and if you have feedback on that objective, we'd love to hear from you on that. Again, we're trying to build an initiative that it's very inclusive and for those who want to be able to be part of the program. So I mentioned earlier about how from the December workshop, we came together to be able to put together a number of projects that we put forward under the Clean Growth Initiative. And it was not possible through the Clean Growth Program to put together one large initiative. So we had a number of ones, and there were small teams that were formed. And I think a number of them are very exciting, and they all kind of touch on various different aspects of mining value from waste. So there's a bioprocessing one for mine waste. There's one looking at total resource utilization from mine waste. Another one looking at cobalt extraction from historic mine waste. And then, several others looking at how we can extract value from different types of waste. So this was the initial start in which where we went forward. And again, a number of these teams have already been working away here at CanMet, but also across the country. So we're going to get into a little bit of both the technical side of things just after we are going to move into our next poll question. So I'll put it back to Bridget to ask the next poll question.
Sure. So the next question here is, what tailings waste type offers the best potential for reprocessing, repurposing? High-risk tailings, gold oxide tailings, low sulfur tailings, waste containing critical metals, excuse us, and reactive pyrite tailings. My apologies. So please vote. Let's see. Okay, 40 of you voted, 40%, 50. Still a little bit of time. Let's see where this goes. Can we get to 80% of you? I don't have the music, the Jeopardy music, but I'll give you a few more seconds. Let's see if there's anybody else coming in. Okay, I think we're about done. So here I'm sharing the results. So the first was waste containing critical metals, followed by gold oxide tailings.
Great.
All right, and back to you.
Thank you, Bridget. Now I'm going to pass it on to Rory, who's really going to present all the exciting stuff, the technical details. Over to you, Rory.
Well, the first step when we started this program was to do a literature review and dig up some case studies. So here we have a number of tailings reprocessing case studies in various stages of planning and production. There are not a lot of details in the open literature about these operations. Most of the information actually comes from the financial filings of the individual companies. We saw that several different technologies have been used or proposed, including improved flotation, heap leaching. Heap leaching is actually quite a large one for particularly gold oxides, and as well as bacterial leaching. And there are many planned past reprocessing operations in South Africa for gold, platinum, and uranium, but there's almost no available information on these operations. There does seem to be common factors between successful reprocessing operations. Mineralogy, value per ton, and tonnage of the material all have a big impact on economic feasibility. But at the end of the day, it's not all tailings can be processed economically, and choosing your material is of utmost importance. Now I'm going to present some of the work that we've been doing here at CanmetMINING. The first project is on bacterial leaching of apatite-rich tailings. There are both environmental and economic reasons for processing this material and reprocessing some of the historic apatite-rich tailings around the Sudbury region and other places. The first reason, large quantities of apatite are being produced at operations during nickel extraction and concentration, and there's significant value in this material with an average grade of 0.8% nickel. At $12 per kilo, that's $100 per ton rock. With negligible mining and milling costs, it's simply slurry and pump. Some of the historic material may contain more than $200 per ton in value, and in addition, some of the apatite tailings have significant cobalt PGE content, making it even a richer material. And the second reason is that it's a highly reactive sulfide mineral that will produce AMD if not properly managed. We worked with 2 apatite tailing samples from the Sudbury region. The results of the chemical and mineralogical characterization are shown in front of you. 2 characteristics led us to believe that we may be able to upgrade the nickel content of the material using mag separation. And those are, the first one, the nickel content of the apatite, which is higher than the bulk material in both cases, and the presence of primarily monoclinic apatite, which is strongly magnetic. We used a wet drum magnetic separator with 1 sample. Our basic hypothesis was that monoclinic apatite and the locked pentlandite would report to the mag fraction. As a result, the nickel content of the mag fraction would be significantly higher than that of the non-mag. We were able to increase the nickel content in the mag fraction, as you can see, but not as much as expected. We characterized the 2 fractions and found several reasons for the lower than expected results. The first one being most of the pentlandite actually reported to the non-mag fraction, indicating that it wasn't locked in apatite, it was actually free. And second being often the hexagonal and monoclinic apatite forms were found to be intergrown, and mixing mag and non-mag in the same particle makes magnetic separation significantly less effective. In addition, the nickel preferentially partitioned in the non-mag hexagonal form, which is non-magnetic. The close intergrowth between the apatite forms and the preferential partitioning of nickel are shown in this nickel X-ray map of apatite grain shown on your screen. At this point, we're not sure if magnetic separation improves the overall process economics. There is also a question if leaving some of the apatite in the non-mag fraction negates some of the environmental benefits, so this has to be further studied. We conducted a number of stir tank bioleaching experiments at constant pH and used surface response modeling and analysis of variance significant testing to assess the effect of temperature and pH. We tracked the concentration of the primary metal values, nickel, cobalt, and copper, as well as the primary nuisance metals, in this case iron and silica. Here we have a response surface of nickel extraction as a function of temperature and pH after 14 days of bioleaching. At both 40 and 50 degrees Celsius, nickel extraction plateaued after approximately 7 to 10 days, whereas nickel extraction plateaued after 14 days at 30 degrees. All bioleaching experiments resulted in 80 to 90% of the nickel being recovered in 14 days, suggesting a relatively robust process over the pH and temperature conditions examined in this study. Here we have the cobalt extraction as a function of temperature and pH. Cobalt extraction essentially mirrored nickel extraction, although with slightly lower extractions at the higher pH levels. And it's expected that cobalt and nickel would follow each other because they report to the same mineral, and they also have very similar metallurgy. So in conclusion from these experiments, there are significant environmental and economic drivers for developing a process to treat pyrrhotite-rich waste that are currently being sent to the tailings. Upgrading with magnetic separation was successful, but it's not clear if it's economically advantageous. The stirred tank experiments that we conducted demonstrated relatively good nickel recovery in the order of 80 to 90% nickel in 14 days, suggesting a robust process, but there is significant room for improvement. A preliminary TEA was created in order to was used to create an order of magnitude economic model, and the results will be used to drive future R&D on this topic. The second project I'm going to talk to you about is RE and scandium recovery from fly ash. Again, this is work we're doing here at CanmetMINING as part of our RE and chromite initiative. So why are we doing this? Why worry about critical metals from fly ash? Well, some coal fly ash materials have RE contents in the range of several $100s per ton, some as much as $500 per ton, in fact. They're strategic metals that are required for clean tech, so it's really there's a driver to develop domestic production of these metals. Many of these wastes do not have high uranium and thorium content, which currently plagues RE potential producers, and it had relatively low capex and opex, so no crushing and grinding. Infrastructure is already at site, and these materials are often amenable to atmospheric tank leaching with mild conditions, which basically is a very cheap process. And one of the most important reasons is fly ash has an end use. It's used extensively in the cement industry, which means we completely eliminate the waste, which is a really attractive feature. So far, we've looked at RE leaching from 4 different fly ashes and 1 bottom ash. At current market prices, the values per ton are in the range of 120 to 200, and with the recent upward movement in rare earths, it might be as high as 250 at the moment. And there are also interesting levels of other metals such as chromium and nickel. It should be noted, though, that a significant portion, anywhere from 20 to 80% of the value actually comes from scandium, because scandium is quite an expensive metal, and it's weathered the economic storm in recent years. We completed comprehensive shake flask leaching studies with 2 of the fly ash samples, examining the effect of temperature, different acids types, acid strengths, leaching time, and pulp density. We really wanted to get a handle on the different factors that affected the leaching. Here we have the results of the leaching test with 1 of the fly ash samples with sulfuric acid. The 3 graphs are ordered from the most aggressive conditions on top to the least aggressive conditions on the bottom. As you see, the majority of the leaching occurs within the first day. There are 2 interesting trends. The first is that the process is relatively insensitive to both acid concentration and temperature over the range tested. And the second interesting trend is preferential leaching of the heavier elements, so we're actually getting fractionation as we're leaching. So in terms of some significant observations from the screening experiments, similar trends were observed with all 5 coal ash samples using sulfuric acid. The REEs are distributed between a readily leachable fraction and a very recalcitrant fraction, and the leaching of that leachable fraction occurs very rapidly. The RE leaching is relatively insensitive to sulfuric acid concentration and temperature. We also tested these materials with hydrochloric acid and nitric acid, and the results are very similar. So we've selected sulfuric acid for further testing because of the relative cost and the fact that recovering REEs from sulfate media is fairly well documented. So we did some follow-up short-term leaching experiments that were conducted in temperature-controlled reaction vessels with aggressive overhead stirring. The fly ash sample was leached with 1 normal sulfuric acid, 20% pulp density, at 4 different temperatures with a couple of replicates at the center point. These short-term kinetic experiments are essential to determine the scale-up factors and establishing experimental parameters for testing during the continuous operation we'll hope will be later on this year and early next year. Here we have the leaching of scandium in 3 REEs as a function of leaching time. The results for the other REEs are very similar. Most of the leaching occurs in the stirred tank occurs within the first hour or two because the conditions are very aggressive and higher Reynolds number. Typically 25 to 50% of the individual REEs leach during the first 24 hours. The initial rate of extraction for all the elements assayed increased only slightly with an increase in temperature, suggesting a relatively low apparent activation energy. It is unclear if the incomplete leaching of the REEs are a result of them being in different carrying phases or a result of incomplete liberation. Further testing is underway to elucidate the reason for these results. The rapid kinetics and the low activation energy suggest a low temperature process with a short solid retention time is suitable to leach a significant fraction of the REEs from this material. The total RE concentration in the PLS is not expected to be above several hundred ppm, so neither direct precipitation nor solvent extraction are suitable technologies for recovering the REEs at these low concentrations. Ion exchange considered to be the only viable option to us. The resin screening experiments consisted of 1 gram of resin with 100 mils of PLS in a flask and letting it mix for 24 hours. The PLS that was used for these experiments was made by combining leftover PLS from the previously described experiments, and that's to really replicate all the conditions. We didn't see much use in using synthetic solutions. Since scandium accounts for more than 50% of the contained value in this material, it was proposed to develop a 2-step IX process where scandium would be removed in the first, followed by the removal of the remaining REEs in the second step. 6 resins were tested in total. This figure shows the percent removal of several elements from the PLS after 24 hours. 2 resins were found to be selected for RE, or for scandium rather, while not retaining any of the other metals to a significant degree. In fact, resin 6 removed almost 100% of the scandium while retaining almost none of the other metals in the solution. As noted earlier, one of the more important aspects of reprocessing coal fly ash is the fact that it may be possible to completely eliminate the process waste, as long as the leached residue is suitable to use as a supplementary cementing material. In order to test this, we used ASTM standard C618 to assess the use of the leached fly ash for use as a supplementary cementing material, according to the test as listed on your screen. Here we have the results of the cementation replacement experiments with 2 different cements. The ASTM standard requires the water demand be less than 105% of the control, and both the 7 and 28 day compressive strengths be at least 75% of the control. As you can see from these 2 tables, the water demand is acceptable in both cases. With the first cement, both the 7 and 28 day compressive strengths are inadequate, as highlighted in the screen, which means that neither the original fly ash nor the leach material nor the leach residue are suitable to use as a replacement with the cement 1. However, both are suitable to use as a replacement with cement 2. In fact, the leach material actually produced higher compressive strengths, albeit slightly, so it actually indicates that leaching the material produces a fly ash residue that's actually performs better in the cement. Here we have the proposed flow sheet. It's very simple: atmospheric leaching followed by ion exchange to recover the REEs. And then the fly ash goes to use in the cement industry, leaving a process with almost zero waste. In terms of conclusions from our fly ash study, from the short-term kinetic experiments, we leached 25 to 50% of the REEs within the first hour or two, with mildly acidic and moderate temperatures, with low apparent activation energy. So it really suggests a low energy process is suitable for this processing this material. We started the development of a two-step ion exchange process. We screened 6 resins and 2 were deemed suitable for further work. And we conducted a preliminary cementation experiments to evaluate the least residue as an SCM. And that residue, one of the residues, performed quite well for several engineering purposes. And now I'm going to turn it back to Janice for her closing remarks.
So this brings us to the end of our presentation. We feel that the Mining Value from Waste initiative has the potential to be a big game changer. You know, as we see that discoveries are less frequent, ore grades are going down, there's an opportunity for us to look at extracting value from existing wastes that are impacting the environment, but also have social impacts as well. So there are many, many opportunities here for us, as I said, the collective, to be able to move forward. But of course, there's also the technical and regulatory challenges that need to be overcome. And that's something that we're hoping to work together with individuals, hopefully individuals that are on this webinar and others in collaboration to be able to kind of advance this initiative and to work out solutions and develop some demonstration projects in and around waste reprocessing and repurposing. So with that, well, we'd love to move into some questions and some discussion and hopefully some answers, and thank you very much for your attention. Back to you, Bridget.
Well,
Janice. Yeah.
I'll transfer to Laura. Yeah.
There you go. Well, Janice, it looks like we do have a few questions here. The first question is, how can I get involved in the Mining Value from Waste initiative?
So we're certainly very interested to have anybody who wants to be involved to be part of the program. So right now we're looking at capturing who's doing what, where. So I would say the first thing is reach out to Rory and I. Our emails are on the screen now, and send us a note and saying, you know, here's the aspect of the work that I see I can contribute. This is what I'm doing. How can I include that in the overall program? Ultimately, we're going to try to grow this initiative and, you know, be able to seek larger funding larger amounts of funding for the program. Right now, it's kind of, we're starting off small, so it's been 1 year. But if you're interested, by all means, love to hear from you. Just email us.
Very good. We have another question. What type of bacteria do you use? Only acidophilic or thermophiliac as well? That's a two-parter. And are you considering e-waste?
I'll start with the e-waste. We're not considering e-waste because it's there are a lot of different groups around the world working on those types of waste, and it's kind of outside of our area expertise, which is rocks and minerals. With regard to the second question about the bacteria, so basically at 30 degrees, we're using mesophilic iron and sulfur oxidizers. And then as we get up to 40 and 50, we get into thermophiles. So yes, we use both, and they have different nutrient requirements.
Okay, very good. And here's another one that just came in. Are you looking into international collaboration? I'm a Canadian currently working in the university in Finland.
Absolutely, we'd certainly be interested in doing international collaboration as part of the research arm of the federal government. It's very easy for us to do a lot of international collaboration. So as I said at the beginning, we do not want to be duplicating effort. We want to advance this initiative, I think globally, ideally, for the global mining industry, and by working in collaboration with others. Certainly in Europe, there's been a lot of work done in the area. Also in South Africa, lot of work that's already taken place on different wastes. So we were very interested in collaborating.
Very good. Okay, boy, the questions just keep rolling in. What is the feasibility of using cyanide as a leaching agent for reprocessing flotation tailings?
So currently we're doing some work on looking at reprocessing some of the gold tailings, and after doing some various work, we've done some cyanidation on being able to extract the gold from the tailings. It's been very successful. We're also looking at the non-cyanide alternatives as well.
Very good. Okay, I have another. We have time for a couple more questions here. How open is the initiative to work developed abroad with small-scale gold mining?
I can't answer again. We're open to certainly have that discussion, and there's a little bit of lack of detail there, but reach out to us with some specifics, and we could have a more fulsome discussion on that.
Absolutely. Here's another one. What are some of the regulatory barriers to reprocessing mine waste?
We've actually done a bit of a quick little study on that, on the terms of looking at the regulatory barriers. And there really is not regulatory barriers. An environmental assessment process would likely be needed. We actually had a slide on it. I don't know if we included it in our, is it in the annex?
It might be.
Yeah, so it might be in the annex. No, we could, do you want to speak to it? I guess we don't have it. No, we took it. But yeah, so we've done a little bit of work on that, and it's not terribly, there's not necessarily a barrier, but I think a lot more discussion needs to happen in and around with the regulatory organizations to be able to move this forward. When our initial assessment is that it requires an environmental assessment process. No worry there anymore. Primary economic, yeah. But a lot of times the risk of, the transfer of liability is one of the things that certainly limits individuals or organizations going in to look at reprocessing. That's another thing altogether.
And we have another one that just popped in. Do you experience problems maintaining dissolved oxygen in treating gold with respect to autoclaving?
We haven't, with the materials that we've been working on with here, we have not been using an autoclave, so it hasn't been an issue for us. We've only been using bottle roll and stir tanks.
Okay, very good.
But it certainly can be.
Right. Okay, well, it looks like we're running out of time, but what I'll do is I'll hold on to these questions and I will send them to our presenters. If you have further questions, please send them along via email in our survey or to our presenters directly. I will turn over to Nolene to wrap up. Thank you so much.
Thank you everyone for joining us today, and thank you to Janice and to Rory for an interesting and informative presentation. We hope that you can all make it to the next presentation we have in the series that will be held on the 27th of June and will feature Rory Wiemeyer. Please take a look at the website metsoc.org, and there you can find further details and register. So thanks again everybody, and we'll see you next time.
Bye.
Thank you, everyone. Have a good afternoon.